Hello everyone, welcome to this video lesson. In this video lesson, we would like to talk about binding energy and packing fraction. We have learned and discussed in the previous video lesson that there is a difference between the mass of nucleons and mass of nucleus, and that is called mass defect. So mass defect we have explained as the previous video lesson as mass of nucleons minus mass of nucleus. So delta M is mass of nucleons means mass of protons and neutrons. We know Z is the number of the protons multiplied by mass of the proton will give you the total mass of protons. A minus Z is the number of the neutrons multiplied with the mass of the neutron will give you the total mass of nucleons minus mass of the nucleus is capital M. This is called mass defect. This mass defect contributes to the stability of the nucleus by converting itself into energy, as we have explained that in the previous video lesson. That is called binding energy. So binding energy can be expressed as delta M into C square as per the Einstein mass energy relation, or if delta M is expressed in atomic mass unit, we know that 1 AMU has an energy equivalent to approximately 931.5 million electron volts. That implies binding energy in terms of AMU, if mass is in AMU, delta M in terms of AMU multiplied by 931.5, so entire answer becomes automatically million electron volts. This is what we have discussed even in the previous video lesson also. So binding energy gives stability to the nucleus. Some mass of the nucleons is sacrificed and is converted into energy. That energy is keeping and binding the nucleons together. That's called binding energy. But anyway, binding energy cannot be exactly a measure of stability of nucleus. Measure of stability of the nucleus. Why? We get the total binding energy, but being a higher binding energy doesn't give a guarantee that the nucleus is more stable. Why not? High binding energy, no guarantee of stability of the nucleus. Why not? That's a question. It is simply not having the high binding energy. What is the job of that binding energy is also an important. Binding energy has to bind the nucleons together. Say for example, some element is having higher binding energy, but there are more number of the nucleons inside that it has to keep together. Then binding energy per nucleon is not enough to keep the nucleus stable. In the other way, say for example, there is a person X and there is a person Y. This person is earning, say for example, something like 40,000 rupees per month. This person is earning only, say for example, say 30,000 rupees per month. Just by looking at this salary, we cannot say this fellow is financially more comfortable than this fellow. You have to ask, how many family members are there in his family? Say for example, there are 5 family members. He, his wife, 3 kids. There are 5 family members. So per person, how much this fellow can spend? 40,000 by 5. That's going to be only 8,000 rupees per person. But look at the Y family. Assume that there is only 3 people in the family. Then per person, the person Y in his family can spend his whole money is 30,000 for 3 people. So per person it is 10,000 rupees. So have you seen? Though fellow is getting a lesser money per month, his family is financially more comfortable because it has to be shared across less number of the people inside a family. Exactly the same thing that what I am trying to tell now. It's not the high binding energy that is important. How much that binding energy has to be shared across the nucleons is important. Therefore, stability of a nucleus can't be measured basing on binding energy, rather can be measured basing on binding energy of the total nucleons per nucleon, like per family member per nucleon. So if the binding energy per nucleon is more,